Hello, welcome to my talk on understanding the static pressure in fluids and in water. Superficially, this topic would be quite easy, but in fact, understanding what causes fluid pressure is not that easy. This talk will give an explanation on what causes the fluid pressure, or what is fluid pressure. Then I will present the historical views on the understandings of fluid pressure and build the equations for static pressure for fluids, and from which we can see clearly what could cause the fluid pressure. And then I move to the calculation of the static pressure in water, as well as the buoyancy created by the fluid pressure, the Archimedes principle. Pressure is defined as the force applied perpendicular to the surface of an object per unit area. The average pressure P bar would calculated as delta F divided by delta S, see here. Or we can define the pressure as the limit of the ratio delta F over delta S when delta S is close to 0. Then we may have a question. What is the pressure in fluid? Since in fluid we may not have a solid surface. In some textbook, the fluid pressure is defined as the surface of an immersed body is bombarded by the large number of fluid molecules randomly, so to create force on the surface. See this picture. The fluid molecules, the black dots, would move randomly and hit the surface of the solid structure, so to create the pressure on the surface. In another textbook, it is stated the normal force exerted on a surface due to the time rate of change of momentum of the fluid molecules impacting on that surface. Superficially, this statement makes sense for the fluid pressure, but when we use it for explaining some practical problems, we could have problems for the definitions. This is an example. We can use the previous definition to explain why a larger pressure would be in a deeper water. According to the explanations of fluid pressure in the previous slide, we can imagine two possibilities for a large static pressure in a deep water. We may have more fluid molecules to hit the surface in deep water. This could also mean the corresponding fluid density would be larger there. Therefore, this is not correct. Or we may say the molecules move faster in deep water, which would hit the surface harder, thus to create large pressure. However, this could mean a higher temperature there. Obviously, this is not correct either. In this talk, we will see what actually causes the static pressure and how people understand the problem, including those who had contributed a lot to fluid mechanics. In the following slides, some historic views on pressure will be presented. We start from Archimedes, from the ancient Greece. Archimedes was a Greek mathematician, physicist, engineer, inventor, and astronomer who made some important contributions to fluid mechanics. The most famous one would be his law of buoyancy, or Archimedes' principle. A body immersed in a fluid experiences a buoyant force equal to the weight of the fluid it displaces. We will see later in this talk, the buoyancy caused by fluid actually is caused by the fluid pressure. This may be the only concept from ancient Greece that the modern fluid dynamics is still using it fully. Or we can say the Archimedes principle works very well for all cases, without any exceptions. I will talk more about the law of buoyancy later in this talk. In addition to this, Archimedes had almost a correct conception of pressure. He stated, in fluids, each part is always pressed by the whole weight of the column perpendicular above it. But today, this understanding is only partially correct. We'll see this later. The second example is Torricelli, who was an Italian physicist and mathematician and a student of Galileo. In 1643, he carried out a famous experiment, the vacuum experiment. In the experiment, he filled a small tube with mercury fully, and all the air in the tube was removed. Then he put the tube upside down and the opening end of the tube into a ball of mercury. The mercury in the small tube lowered to a certain height, 760 millimeter height above the mercury surface in the bowl. Now we often use this mercury height to calculate the atmospheric pressure P0. In this experiment, Torricelli could prove some important things. The first would be the determination of the atmospheric pressure, which is calculated using the mercury height. It's now given at this P0. And another important thing for this experiment was that he created a vacuum in the top of the small tube, see here, which is a phenomenon that ancient Greeks thought impossible to achieve. In fact, this experiment proved that Archimedes' conception of pressure would be only partially correct, because regardless how large of the tube we are using, the height of the mercury in the tube would be always the same. Thus, it is not the whole mercury weight for the pressure. Then we have Blaise Pascal, who was a French mathematician, physicist, inventor, philosopher, writer, and a Catholic theologian. Pascal is famous for his barrel experiment, named the static experiment. It was supposed the experiment performed in 1646. In the experiment, Pascal supposed insert a long vertical tube, this tube, into a barrel filled with water. When the water was poured into the vertical tube, the increased static pressure could cause the barrel to burst. I saw this picture from my textbook in the secondary school, but in fact, there was no historical record to show Pascal actually performed such an experiment. However, this experiment shows that even the weight of the fruit in the small tube is small, it still caused a very large pressure in the barrel, so to cause the barrel to burst. This somehow contradicts with the Archimedes' conception on the fruit pressure. The whole weight of the fruit above causes the fruit pressure. Another contribution to understand the pressure is the Pascal's law, which states that the pressure applied to a surface of a fruit would be transmitted uniformly throughout the fruit in all directions. A famous application of this rule is the hydraulic jack, for which we can apply a small force F1 here because of the small cylinder. Thus, this small force could cause a large pressure, and this large pressure could be transmitted to this large cylinder. Thus, it causes a very large force, F2, to lift the car. Hence, by using the hydraulic jack, we can easily lift a car. Euler was a Swiss mathematician, physicist, astronomer, geographer, logician, and engineer, who made many important and influential discoveries in many branches of mathematics, and he is generally regarded as one of 4 greatest mathematicians in the history, along with Archimedes, Newton, and Gauss. He also made some very important contributions to fluid mechanics, for which he laid the foundation for the theoretical fluid mechanics. This would include: he was the first person to recognize that the pressure in a fluid is strictly a point property defined as this. We have seen this definition before. And he presented very well the fluid pressure in building the fluid dynamics equation. This includes the Bernoulli's equation, for which he actually derived it, although this equation bears the name Bernoulli. And now, the Euler's Bernoulli's equation is a general form of the relation between the fluid velocity and the fluid pressure, which is still the most applied equation in fluid mechanics, although it is for inviscid flows. Euler also derived Euler equation in 1757, the general fluid dynamic equation for inviscid flows. It was Euler equation enabled Navier-Stokes and many others to fully establish the fluid dynamics equation by adding the fluid viscosity effect into the equation. It must be emphasized, although the fluid dynamic equation is named as Navier-Stokes equation, the foundation of the fluid dynamic equation is actually the Euler equation. Now we will see how the pressure equation is built for fluid. We consider an element of the fluid, the rectangular box, with the sides delta x, delta y, and delta z. We first look at the force balance in z direction. And we see here the pressure P is supposed at the center of the element. So on the lower surface, the pressure is calculated as P minus the pressure gradient times half delta Z. This is because the distance from the lower surface to the center is minus half delta Z. Similarly, for the pressure on the upper surface, it is calculated as P plus the gradient times half delta Z. So we can build the balance equation based on the force balance. This part is the buoyancy due to the pressure difference. And the minus sign means the force due to the pressure is in the opposite direction with z-axis. And this part is the fluid weight of the element. The minus sign means the fluid weight is in the opposite direction with z-axis. So we can simplify this equation into this simpler one. The first term is from this large ellipse, and the second term is for the fluid weight. And we can cancel out delta z, delta x, and delta y. So we could obtain the equation for the pressure gradient in the z direction, the partial differentiation of pressure with regard to z equaling to minus rho g. This is a pressure equation for any fluid, since in here we didn't assume whether the fluid is liquid or gaseous. Thus, the equation would be correct for all fluids. Similarly, we can look at the pressure equation in x and y directions. In x direction, we could build the equation as this. This actually is the forces due to the pressure on the front and the back side. And these two forces are balanced each other. And in y direction, the forces due to the pressure would be balanced themselves. And these two equations can be simply given as the partial differentiation of P with regard to x and P with regard to y are both zero. This means in the static fluid, if the coordinate is put in this way, z is pointing vertically up, the fluid pressure would be a function of z only, is independent of x and y. Therefore, the partial differentiation of P with regard to z would be same as the normal differentiation of P with regard to z. So these two equations are same for the fluid pressure. In this slide, we are trying to look at how we can observe the static pressure from the pressure equation. Basically, we can calculate the pressure by integrating this equation directly. So we have P minus P0 equaling to the integration from Z0 to Z1. Here, P0 is the reference pressure at Z0. In many practical applications, P0 would be the atmospheric pressure at sea level, where Z0 would be 0. We can write the pressure increment P minus P0 in a form of summation given as this. So this summation would be equivalent to the slices of the fluid element. So we can see many slices from Z0 to Z1. So sigma would be the whole weight of the fluid slices. And each slices, the weight is rho g delta z. This means the column would have a unit horizontal area. So we can see the pressure is linked with the weight of the fluid of unit horizontal area. However, in this form, the understanding of the pressure is still not very clear. In this slide, for a better illustration, we take a z-axis pointing vertically down. As such, the pressure equation would be given as this. Because of opposite z direction, so the minus sign here is dropped. So we can calculate the pressure difference from Z0 to Z1 given as this P minus P0 equaling to the integration from Z0 to Z1. We can write this integration into a form of summation. So this would be given as this. And the expression in here is actually for the fluid slice. And each slice has a weight of rho g delta z. That means the slice has a unit horizontal surface. Now we can understand that the pressure increase is due to the whole weight of the column of unit horizontal area perpendicularly above it. So when we compare this statement with the statement of Archimedes, the difference would be here the unit horizontal area, not the whole weight of the fluid perpendicularly above it. So from this, we can understand the pressure is caused by the fluid weight of unit horizontal area. Here in this slide, some facts about the water are given. In the deepest ocean, about 11 kilometers deep in the sea, the gravitational acceleration changes less than 0.35 when compare the gravitational acceleration at the surface on the Earth. Water density changes would be very small, even in a very large static pressure, say 1,100 bars. This is the pressure actually in the deepest ocean. It would cause the density change less than 5%. In the natural world, such as in lakes and seas, the water temperature would always be between 0 degrees to 30 degrees Celsius. Such a temperature, the water density is almost constant. See this plot. The change of the water density would be less than 0.4%. Thus, we can assume that in the natural world, both the water density and the gravitational acceleration can be regarded as constant for most practical applications. This would be very important since this can much simplify the water pressure calculation. And another fact is that the pressure gradient in water would be about 10,000 pascals per meter. The minus sign here means the pressure would decrease with that increase. As per the facts presented in the previous slide, the water pressure can be easily calculated by integrating this equation directly, since the water density and the gravitational acceleration are both constant. So we have the pressure expression for P equaling P0 minus rho Gz. P0 is generally taken as the atmospheric pressure at sea level if the coordinate origin is put on the sea level. And we can take h equaling to minus z as the water depth, see here. So we have the pressure given as this P equaling P0 plus rho gh. Or we can have the gauge pressure delta P equaling P minus P0. It is proportional to the water depth H. So we can see the black dashed arrows for the gauge pressure in water. In the next few slides, a discussion will be made to Archimedes' principle, the law of buoyancy. A body immersed in a fluid experiences a buoyant force equal to the weight of the fluid it displaces. To show the principle, we look at a rectangular body in fluid with the top-bottom surface delta S equaling to delta X times delta Y. The pressure difference between the top and the bottom surfaces would be calculated as P2 minus P1 equaling to this integration. And the integral is from Z1 for P1 to Z2 for P2. The buoyant force is actually caused by the pressure difference, P2 minus P1. This is true regardless what the fluid would be, liquid or gases. The pressure P2 is always larger than P1. So the buoyant force FB is calculated as the pressure difference times delta S. So the force would be upward because P2 is in the same direction as Z-axis. So it would, by the integration, times the surface delta S. And if we change the integration limits, so we have the expression as this. Here, the minus sign is dropped because we changed the order of Z1 and Z2. If we write this integration into a summation form, it would be given as this. And this summation is equivalent to the total volume of all the slides together. And the delta Z is the height of each slide. And this would be given as the summation rho G delta V. Here, delta V is the slide's volume equaling to delta Z times delta S. So from this expression, we can see the buoyant force is equivalent to the weight of the fluid of the rectangular box. That means the fluid displaced by the rectangular box. And the fluid pressure on the top and the bottom would only contribute to the buoyancy, while the fluid pressures on the side of the rectangular box would not contribute to the buoyancy. When we derive the Archimedes principle, we use the rectangular box. However, the Archimedes principle holds for all bodies of any general shape. For instance, if we have a general shape in the fluid, we can use many small rectangular prisms to approximate the body of the general shape, very similar to the way in the calculus. So if the prism is very small, the approximation to the body would be very good. And from the previous slide, each prism would experience a buoyant force equaling to the weight of the fluid it displaces. Therefore, the whole buoyancy of the immersed body would equal to the whole weight of the fluid displaced by the immersed body. This is the Archimedes principle. Now, in the last slide, some more facts on buoyancy will be presented. The Archimedes principle holds for both gases, air, and liquids, water. So regardless how light of the fluid can be, there will be a buoyancy force if the body is immersed in the fluid. The buoyancy force is caused due to the pressure difference in the vertical direction. In fact, there is always a pressure difference in the vertical direction due to the weight of the fluid. For the buoyancy calculation, fluid density can be either a constant or a variable. For instance, for water, the density is always a constant. Water density is about 1,000 kilograms per meter cubic. However, the air density is variable with the altitude, and at the sea level, the air density is 1.225 kilograms per meter cubic. A given body in water would experience the buoyancy force about 800 times larger than in air. This is why for marine structures, buoyancy force is all important, whereas for aeroplanes, it is negligible. For the light than air vehicles, such as the hot air balloons, they can obtain sufficient buoyancy force simply by displacing huge volumes of air.